For question 4 you need to plot a graph. Now I know I forgot to give you some graph paper, so 3 alternatives. Either you've got some graph paper and use that, or you don't have to use graph paper at all because you can always use a spreadsheet. So you can always just stick this data into Excel and get Excel to do the graph. That's fine. Or if you haven't got any graph paper but you want some graph paper and you don't want to go to the shop to buy some graph paper, why don't you print some graph paper for free using the website printfreegraphpaper.com. Honestly, that's the name of the website. And you never guess what it does. It lets you print free graph paper. So if you use the website, the sort of graph paper that looks like we're used to using is what they call engineering graph paper. That's where you've got some thick lines and then some thin lines. And make sure you use A4 in millimetres. Once you've got your graph, you've got to explain what the shape of the graph tells about the behaviour of the material in the wire. Now I haven't done a graph, but looking at the data, I'm guessing that you'll be using words like elastic and plastic and fracture. You might want to say that the material is ductile, if it is. Part C asks you to use your graph to find the Young modulus of the material. Now remember that Young modulus only applies to the elastic part of a graph that's a straight line. So that tells us, without drawing the graph, but you'll have drawn it, that the graph must have a straight line part. So how do we use the straight line part to find the Young modulus? Well, remember the formula, and we take the one from the data sheet, FL over A delta L, and we'll look at the graph. Now if we wanted to, we could read off one value of force and one value of delta L, and we could put those values into the equation. But actually it's much better to use, when a question says use the graph, you should really be using as much of the graph as possible. So what we can do, we can actually use all the points on the graph to find F over delta L. So to do that, we find the gradient, because the gradient of the graph is F over delta L. So we find the gradient of a straight line, that's F divided by delta L. To find the Young modulus, we then need to multiply, so it's F over delta L is the gradient. If we multiply that by L over A, we get the Young modulus. A slight extra complication though, because the extension was given in millimetres, you've actually got to convert the millimetres to metres. So when you work out F over delta L, to find the gradient, you should take the value on the x-axis and you should divide that by 1,000 so that you get the value in metres. It's going to be gradient in newtons per metre. Question 5 looks horribly mathematical and complicated. I'm sure it's not really, so let's try and sort out what we know. The question's about Young modulus for steel and brass, so let's remind ourselves by looking on the data sheet what we mean by Young's modulus. And there's our reminder. Young modulus, it's tensile stress over tensile strain, but as far as we're concerned, the formula we have to use is Young modulus is force times the original length divided by the area times the change in length. So let's write that formula down. Young modulus, which we tend to use letter E for that, is equal to FL divided by A times delta. Now in this question there are two materials, so that's two values of Young's modulus, and there'll be two different forces. But everything else will be the same, because it tells you that the wires were the same length to begin with, the same area to begin with, and because they're fastened together at both ends, the amount that they're stretched by is going to be the same for both of them. So if I write down the equation for each material, if I'm thinking about the steel, I'm going to call the Young modulus of steel ES, and that will be equal to, well, the value for force that's in the steel, I'm going to call FS, but for the lengths and areas, I don't need to use separate letters because there's only going to be one value of L, one value of A, and one value of delta L in the question. I can do the same thing for the brass. Brass has got a different value of young modulus, I'm calling it EB. And the brass wire's got a different force in it. So two wires share the force, but they don't share it evenly. There are different forces in each wire. So the force in the brass wire I'm calling FB. But everything else is the same, because the wire was the same length to begin with, it had the same area, and it's stretched by the same amount. So there we are, I've got two equations. Now what I'm going to do with those equations is I'm going to separate out the things that change, so the young modulus and the force, that's different from the two wires, but everything else is the same. And the easiest way to separate that out is if I take ES and I divide by FS, then those are the two things that are different for the steel, and it will equal L over A delta L. I can take the young modulus of brass, I can divide it by the force in the brass, and that will also equal L divided by A times delta L. And at this stage I've suddenly realised I'm supposed to be giving you hints, I'm not supposed to do the question for you. So I'm not going to go any further, except to tell you that hopefully you've spotted that these two things are the same. And actually we're not interested in any of those things. But if that's the same as that, then it also means that that is the same as that. So you should be well on your way to answering the first part of the question. For part 2, it asks you to find what the value of Fs is when the total force is 15 newtons. So if you look at this formula, that formula tells you how Fs and Fb compare. Because Fs divided by Fb is the same as Es divided by Eb. And it tells you here the values for Es and Eb. So you can put those into the formula, work out Es over Eb, and whatever number that gives, that will tell you what Fs divided by Fb is. And you know that the two forces must add up to 15 newtons. And you know how the two forces compare with each other. So you should be able to work out what Fs is. And it has actually been made very easy. There is actually a very simple ratio in there which hopefully you'll spot. And for part 3, by the time you get onto part 3, you know the force in one of the wires. The question tells you the area, it tells you the unstretched length, you know what the young modulus is. So if you come back to this original formula, all you need to work out is delta L. And although in an exam you'd only do it once, because it's not an exam and you've got a week's holiday to do it in, it's probably worth checking that you get the same answer whichever wire you use.